I can't hear you anymore. Katie, it looks like your status got moved to offline all of a sudden, which is funny because we were just chatting. But maybe if you turn your mic back off and on again, maybe that'll help.
Hi, am I back now?
There we go. We got you.
Oh, I'm so sorry, everybody. I am having to use a hotspot connection, and it is a little spotty. So hopefully that'll be cleared up now. I apologize if it goes in and out a little bit.
No worries. I think we lost you again.
Oh, I'm so sorry. I'm really not sure how to.
So I think we lost you. I am wondering, let's try something different. Why, if you're able, if you can switch to phone audio where you call in, you should be able to use the little audio drop down in the dashboard, and that should give you a phone number when you switch to phone call. Let's see if that helps.
And so I'm going to be talking about my thesis work using dual drainage modeling to assess impacts of green stormwater infrastructure on events of roadway flooding. Some background on this. Urban flooding is flooding that occurs when the stormwater network is inadequate or is aging and is losing capacity or is clogged. And so we just have too much water going into a system that can't contain all of it. And so urban flooding occurs. This is distinct and different from coastal flooding or flooding due to rivers. And but it does cause a lot of damages and to property and infrastructure, and also it really is a risk to human health and safety. The National Weather Service estimates that this type of flooding caused $7.9 billion of loss between, on average, between 1980 and 2013. So it is a significant loss. And it's also important because it disproportionately affects communities that have fewer resources. A study done by Texas A&M and the University of Maryland that surveyed 350 different municipalities found that 50% of flooding occurs in low to moderate income housing areas, and an additional 20% occurs in
Katie, you cut out again. I'm assuming it's not just me.
So then I am looking specifically at roadway flooding, and roadway flooding is often falls in the category of nuisance flooding, which is much smaller than the larger sort of catastrophic flooding that you might be thinking of. And this is flooding between 3 to 10 centimeters. So like you can see in the picture, cars can even
Hey, Katie. Katie, we can't hear you. I'm not sure if you can hear me, if there's a bandwidth issue. Hey, Katie.
Sorry. Yeah.
Can you try switching to just your telephone instead of using your computer audio?
I think the issue is that my internet is not staying connected. So just because it is a
So yeah, you cut out again. I'm wondering if
is it in and out a bunch, or is it, are you missing big chunks of what I'm saying?
there's big chunks that are missing.
Oh,
So
shoot.
I'm wondering, if you call in on the phone, you could still talk through your presentation, and then if there's a lag in the slides, it's not the end of the world. At least we can still hear what you have to say.
Okay, yeah, I will give that a try. I'm so sorry, everybody, about all of the disconnection.
No worries. You know, it could also just be a system bandwidth issue. You know, the go-to platform's pretty popular these days, so.
Okay, can everybody hear me now?
Yes, that sounds a lot better.
Okay, thanks for patience, everyone. It's a whole new world having to do everything virtually.
Yeah.
Okay, so am I still sharing screen here?
You are. It's not in full screen mode, but it's the roadway flooding slide.
Okay, I need to do the presenter mode, and then we will be good to go, I think. Okay, are you guys seeing the roadway flooding?
There hasn't been a change in the display. It could be a little bit laggy though.
So you're still seeing the display setting one?
Well, I'm just seeing PowerPoint with your notes, but not the presenter view. There you go. Now I have it. So it could.
Screen, so it was going back and forth to which one I was sharing, of course. Okay.
I think you need to flip it back. I think there's a lag. So now it's the presenter mode. Sorry.
Oh no, okay, this is my fault. I'm sorry for everybody that's having to listen to my technical difficulties. Okay. Are we working with the good things now?
I think there's just a lag because of your hotspot. So you just start talking and we're gonna go with the flow. Pun intended.
Okay, sounds good. So we are talking about roadway flooding, and just to kind of get caught back up. So we're talking about nuisance flooding, which is smaller scale flooding, and a potential strategy for addressing this type of flooding in urban systems is green stormwater infrastructure, or GSIs. And for people that may not be familiar with it, these are stormwater technologies that typically use infiltration or collection to reduce or slow down how much water is entering into the typical stormwater network. So that's you're thinking like pipes underneath the road surface, or just subsurface pipes. And so studies have been on single or small scale networks that show that they do mitigate smaller storm events, that they are effective for these purposes. And then there's also been studies looking at placement in the watershed, for centralized being closer to the outfall into the stream, and distributed being across the watershed. And GSIs also pose a unique challenge for implementation and long-term effectiveness. They require very carefully being designed and put in when they're put constructed, and then also they need to be maintained in order to maintain that long-term infiltration capacity. So for my research question, we're looking at what are the impacts of implementing green stormwater infrastructure networks on urban roadway flooding and the resilience of transportation networks. And as I've been working on this project, it's really come down to a question of scale. And so there are components of this that are at the structure scale. So you're thinking like an individual stormwater structure being a manhole or a conduit or an inlet structure, and how these are interacting with each other on like a small scale. So 1 or 2 or 3 inlets working together to collect the water in a certain region, or individual GSIs and how those fit into that network of the normal stormwater system. And then also the size of nuisance flooding occurs at a structure scale. It could happen because of the failure or inadequate capacity of 1 or 2 inlet structures. And then there's also the network scale. So the distribution of network flooding occurs across the entire watershed. It isn't typically isolated to one area, though there may be some very specific problem areas that can be addressed, but usually this happens in locations throughout a watershed. And then the GSI placement has to also be thought of at a network scale. And then there's also calibration with stream flow. In order to calibrate these stormwater models, we have to be able to look at all of the water that may be flowing into a stream and then calibrate that with data from a USGS or similar stream flow gauge. So then how I'm going to approach, or how I've been approaching trying to integrate these 2 scales together, the structure scale and the network scale, is using a dual drainage model. So a dual drainage model allows you to combine 1D subsurface stormwater networks, that's your pipes, inlets, conduit, with a 2D overland flow model. So that's just the water flowing over the surface, including over roads and impervious, non-impervious, or impervious and non-impervious surfaces. And it really, the interaction occurs between the 1D and 2D model components at the inlets and outlets. So you have water flowing into the system at the inlets, and at the outlets, either flowing into a stream or a surface storage area. I'm specifically using a software called PC Swim, which is developed by Kaiwater, and it uses Swim 5, which is I think it's maybe 0.3, but it's the most up-to-date EPA SWIM model, which is the stormwater management model. And part of the reason that we really have gone in this direction of using 2D and 1D integration is that the output is driven by the fact that this research is leading and is combined with research for a traffic model where they're looking at the effects of hazardous conditions on driving patterns. And so the output needs to be spatial depth of flood water across the roadways. So this is an overview of the methods that I'm going to be using to address this question. I'm not fully at complete results. I'm still working on model development, but this is the way that I'm going to address the whole question in the end. So the first part is data collection and processing. This includes filling missing data and adding input parameters that are necessary for modeling the stormwater network. And then the development of the dual drainage model, which includes developing the 2D mesh and connecting the 1D and 2D components. And then calibration using USGS streamflow data. And then determining the placement of GSIs in the network using a strategy called critical link analysis. And critical link analysis is a method where you look at traffic data and flood data in combination and identify points where you're having the most interaction with traffic flow and flooding. And studies have shown that the most effective place to put GSIs is where you're having that interaction with the traffic, if that's what you're trying to mitigate for. So then implementing the GSI network into PC Swim, and then assessing the impacts on flood depth and spatial distribution. And this will be, the end output for the traffic model is that flood depth over the roadway. So the study location I'm using is Harvard Gulch in Denver, Colorado. Kind of hard to see in that little sub map, but it's a watershed located in sort of the southeast area of Denver. And it's a highly studied urban watershed, which is really useful because there are previous reports and models that allow or give a lot of background information and some reference. There's readily available stormwater data. Denver has an open source data set for their stormwater networks and other relevant spatial information such as imperviousness and building outlines and such. Then there's there's two USGS gauges, an upstream and a downstream gauge. Unfortunately, I didn't remember to make those bigger, but there's if you can see my cursor, there's one at the downstream area and then another one at the upstream. So that allows for calibration of the model. And then there's also multiple rain gauges. There's 5 in total across in the watershed, and so that allows for more accurate precipitation data to be used. So now I'm going to talk kind of about some of the challenges that really tie back into that question of the matching of the spatial scales. And so stormwater network data is, of course, one of the initial steps and is quite potentially one of the more important steps in model development. You want to start with good data, obviously. But unfortunately, accurate stormwater network data is harder to come by than you would first expect, and harder to come by than I first expected when I started this project. Oftentimes, there's older infrastructure that may not have made the leap from digitized or from paper as-built documents to digitized stormwater information, and smaller. Sorry, go ahead. Somebody probably just on audio, but or smaller communities have may not have as much stormwater data available, and so the ability to model these networks is really tied to the quality of the data that we have. Denver has has pretty high quality data, but you can still see that the yellow dots show the data that is not being or that does not have any information to it, or does not have any invert data available. So that data has to be filled and fixed. So then to develop the 1D subsurface model, I began by filling and correcting data that I could, and some of the information, they may not have invert data, but it had information on the type of inlets that were available. And so I was able to use the standard specifications from Denver to look at or to come up with a best guess for the information for those inlets. And then I also had to really think about assessing connectivity and simplifying the network without losing detail. In the picture here, you can see it's a fairly complex area where you have the Yale Ave and Colorado Boulevard are coming together. Those are 2 fairly large intersections, and there's also kind of a shopping mall area there. So you get this fairly complex stormwater network that, with the addition of missing data, it's sometimes easier to simplify a little bit than to keep data that is maybe not so trustworthy. So really making decisions about connectivity and simplification while still trying to keep that structure, scale, detail. So then looking at the 2D surface model, this is created using the DEM, and I started by separating the boundary or the roads from the surrounding area, because I'm using a finer mesh on the roads because these are the places that I really want to get that higher resolution roadway flooding data at the scale of, an area that may be flooding due to 1 or 2 of these inlets. But then also doing this over the whole area of the watershed, there ends up being a lot of a lot of mesh cells, and this kind of pushes the boundaries of what PC Swim is able to do. So really trying to get detail without exceeding model capabilities has been a challenge. And then connecting the 1D to 2D model is done using outlets, and these outlets are connected using rating curves, which describe the water, how it would flow into the inlet depending on the inlet geometry and type, and then the height of the water above the inlet. And so that's that little figure in the bottom there that's showing how when the inlet is not full, the water flows over and in, but mostly in, and then if it's full, and then if it's overflowing. And so that's what we're trying to model with those rating curves. So then another challenge for modeling flood data is the lack of validation data that may be available. There is very little, if any, data on the size of flood events in like roadway flooding. And so the way that we're approaching this is using observations from citizens. So this is done through Flood Tracker, which is an app that's developed by people in our research group. You can see the link there if you want to start putting information in as it starts raining all the time. But basically, it's a method of gathering spatial urban flooding data so that we can use that to validate flooding models. And we're also looking at 311 reports, and then we can also look at social media posts to qualitatively evaluate the flooding model. So then, conclusions. As with a lot of things in water right now, the events are going to increase with climate change and urbanization. And if actions aren't taken to mitigate these effects, the impacts will continue to disproportionately hurt communities with these fewer resources. And so to me, it seems that this ability to model and understand where it's best and where our GSIs are most effective, or if they're an effective strategy, is really important to be able to help communities make decisions about the types of infrastructure that they should be putting in place to get the most effect for their potentially limited resources, and really understanding whether GSIs are effective at reducing roadway flooding. It's really important to be able to model that structure scale where you're looking at how a single inlet or a series of a few inlets is going to cause flooding, but how that's occurring over the entire network. Okay, so thank you. Sources, and then if anybody has questions, I don't know how much time we have.
Yeah, I think we could probably make time for one question if anyone has anything pressing. You can get hands or enter it into the chat queue. So I'll just give it maybe 15, 20 seconds, see if anything pops up.
Okay. Yeah, thank you. Thank you everybody for listening and being here, and I appreciate it.
Okay, well, I'm not seeing anything pop up, but if anybody has any questions, you